Yes, sir.
Okay, so this question we were doing, right? So whenever we are charging a capacitor, right? So there has been some work which has been done. So whenever we are charging the capacitor, so we have to do some work to charge that capacitor. So some amount of work, yeah. So we are charging this capacitor, and some work has been done to charge this capacitor. So in this question, we will show that there is some work has been changed to the energy stored, and some work gets released in the form of heat. So some work has been wasted, and that is what we call in the form of heat dissipated. Okay, so you are doing some work. So initially it was uncharged, and you join some battery of, let's say, EMF. So let's say the EMF of this battery is E. So what you do is that this EMF charge this capacitor, right? So there has been some work, there has been some energy change in this capacitor. So some amount of energy has been stored, and some amount of energy gets released in the form of heat, right? So you see that the capacitor gets heated when you charge, when you join it, or when you connect it to some battery. So it gets heat up, right? It will store some energy, and then it will also get heated. So we have to calculate that how much it gets heated. Okay, so let us calculate that, and we know that work is the energy plus the heat. Okay, so remembering this, can you guys tell me that this is initial charge is zero because this is uncharged, and capacitance is C, right? So can you guys tell me that what would be the initial energy stored? What would be the energy stored? Yes. What is the energy stored in this device? That is half CV square, right? And voltage is zero, so this is zero. So initial energy stored is zero. Understood? Understood, everyone?
Yes.
Okay. Now the capacitance of this capacitor is C, right? And the EMF is E. So what would be, because this, when we join this EMF to this capacitor, so it gets charged. So now what would be the charge of this capacitor? What would be the charge? The capacitance is C and EMF is E. So what would be the charge of this capacitor?
Mhm.
CV, right? So CV, which means that voltage is E, so this is CE. Okay, so final charge is C. So if we want to calculate the work done, right? So work done to charge this capacitor. Initially it was zero. Now you have charged it to this much. So what is the change in the charge? That is Q final minus Q initial. So how much you have charged this device, right? So that is CE minus 0, which is C. Okay. And what is the work done, guys? So work done in charging the device or capacitor? So work done is what? This is QV, right? So you are applying a voltage E, and the charge that you have charged, right? So that is delta Q. So this would be V delta Q. So V, you know that that is E, and this is C. So this is CE square. So that is the work done. Is this part clear?
Yes, sir.
So this much amount of work has been done by this EMF, by this battery, to charge this capacitor. Now, some charge has or some work has been changed to the energy stored, and some work has been done in the form of, or some work has been released in the form of this heat. So we have to calculate the heat dissipated. So before we do that, let us calculate the change in energy. So U initial is 0, U final is how much? How much is final energy stored in this capacitor? Yes. What is the energy stored? What is the energy stored in the capacitor? See, your EMF, your battery voltage is C, your capacitance is C. So what is the energy stored in this device?
Half sleeve, sir.
Half CV square, right? So half CV square, and then this is half voltage is E, so half CE square. So U final is half CE square. Okay. So now we know that U final is half CE square. So how much energy has been changed, right? So this is delta U, which is U final minus U initial. So this is half CE square minus 0, which is half square. So delta U is half CE square. And we know that work done is this energy plus heat dissipated. So heat dissipated would be, this would be W minus delta U. So this is CE square and minus of half CE square. So CE square minus half C square. So that would be half CE square. So this is the heat which has been dissipated, right? So this is the heat dissipated in storing the energy of the capacitor, or this is the heat dissipated in charging the capacitor, right? So the total work was this much. Total work was this much, but half changed to the energy storing capacity and half of which dissipated through the heat. Okay, so this is 50% of the total energy. So 50% dissipated, or we can say that wasted or exhausted in charging the capacitor. Okay, so this is what we call the heat dissipated in charging the capacitor. Is this part clear? Yes, guys, is this part clear?
Yes, sir.
Okay, so you guys please note it down and then we'll do one question. Which one? And whenever you guys want me to scroll down the screen, guys, please tell me. So whenever you guys want me to scroll down the screen, guys,
Answer.
done. Okay, so noted, everyone.
Answer.
Please to note this one out. And whenever you guys have noted it down, please tell me.
Done, sir.
Noted. Yeah. Rabia, what about you?
Yes, sir, does.
Okay, so now let us do one problem. We have so a capacitor of capacitance C has been charged to EMF, right? So EMF, which is so initially it has been charged to this EMF. Now it is connected to an connected to a battery of EMF E-byte, right? So then we have to find out first charging or total charge flowing through the battery. Secondly, we have to find out work done by the battery. And thirdly, we have to find out heat dissipated by the capacitor. Okay, so these are the three things we have to calculate. So let me draw the pictures and then you guys solve and then you guys tell. So initially we have, remember it is charged. So we have to keep in mind all these things. So initially it has been charged and its EMF is E and capacitance. So and then it is oh yeah sure. Okay. Hello, Assalamu alaikum Fia. So are you here for the NEET classes?
Sorry, sir, it got late.
Oh, okay, okay. So no worries, no worries. In the previous class you were not there, right?
Yes, sir. I don't know, sir. This time, link is being sent like it was not like Sunday, Monday. We had a schedule, right? I
Oh,
think it was not with that. It was randomly biology, physics, chemistry. So one class will be earlier. Because of that, it did not be. So I
yeah.
thought no class today.
Oh, so you got confused with the time.
Yeah,
So
like
okay,
it, link was not according to the schedule, so I couldn't. I did
yeah.
not understand that.
Oh, okay, okay. No worries, no worries. So okay, so we are just understanding that how much. So we have a capacitor, right? And
Yes, sir.
what we do is that we connect that capacitor to a battery. So that battery will charge that capacitor, right?
Yes,
So,
sir.
so we have to calculate that how much heat is dissipated, right? So because when we charge a capacitor, it gets heated. So some amount of work done goes in charging that capacitor, in storing some amount of energy, and some amount of work done is wasted or is changed to or is released in the form of the heat. So we are just calculating that how much heat is dissipated by the capacitor, right? Okay, so initially, yeah, so when we will do this question, then it will be good. So, but you just, yeah, so Aisha and Rabia, please bear with me for a moment. So, Fia, you just take the screenshot of these. So, we have a
Yes, sir.
yeah, we have a capacitor which is uncharged, right? And
Yes, sir.
and then we charge. So when we then we apply or then we connect a battery of EMF E to this capacitor and then it gets charged. It was uncharged and then it gets charged. So when it is charged, so there is some energy stored, right? Half CV square. So energy stored is half CV square and charge is QV. Charge is CV, right? So
Yes,
we
sir.
so the work done is PQ, we already know. So we calculate the work done and then from the work done, we subtract this energy stored. So then we get the heat dissipated.
Sir, can you scroll up? I'll take a screenshot.
Yeah, so this part you have taken the screenshot.
Yes,
So
sir. Right.
this, this part you please take the screenshot
Yes, sir. Down.
this one. Last one.
Yes, sir. Down.
Okay, so now we are doing this question. We have a capacitor and this has been already charged. So it has initial EMF or initial voltage E and its capacitance is C. And then what we do is that we connect this capacitor to a battery whose EMF is E by 2, right? So then we have to find out that first we have to find out that total charge flowing through this battery, then work done by the battery and then heat dissipated. So this we have to calculate. So you guys please calculate this thing and then yeah, whenever you guys get any answer, so please tell. Rabia and Aisha, you guys solve this part and Fia, you also try to solve, but if you are not able to, then I will explain. Okay. Okay, you have just joined, so just wait for a moment because yeah, Rabia and Aisha, are you guys solving this question?
Yeah.
Yeah, so
Sir, for this, we'll be using C epsilon.
E epsilon, what V epsilon? Okay, so EMF is this is not epsilon.
Sorry, sir.
Not
C
that
EMF.
E unit, which means what? Yeah.
Yes, sir.
So what are you saying?
So, but QF is equal to C.
Yeah, Q equal to C V. This are you saying this one?
Okay.
No, no. What are you saying? So was this your question?
No, sir, that V will be equal to E, right? EMF, right?
Yeah,
So
yeah,
3
yeah,
by epsilon by 2.
yeah. So I'm just representing voltage by this, right?
Yes, sir.
So this is just a representation. I can also represent it by V. So, but we have studied cell, and in cell we understood that we represent the actual EMF by E, and there is some internal resistance. So the total is V minus ER. But we are assuming that we don't have any so E minus IR, but we don't have any internal resistance. So V is actually E, right? Okay, so you guys please calculate these three parts, Aisha and Rabia, and then tell me the answer. Are you guys calculating? or you got stuck at some point, guys? What is Q? What is W? What is what? These things, three things we have to calculate. We have to follow the same process, right? Yes, Aisha and Rabia, got any answer or solving or got stuck at some point? What happened?
Solving some.
Oh, you are okay. So please calculate and tell me the answer. And Pia, you also try because yeah. So just see the screenshots that you have taken. So we are following that same steps. Guys have to always remember these, right. This one that we did, yeah, this part. So always remember this part. What is C, V, Q, E, U? So when you remember this one, then it would be easy to calculate, right? Okay. Yes, guys, got any answer? Okay, so let me ask one by one. And first, we have to calculate total charge flowing through the battery. So first, let us write all the prior information that we have. So in the initial part, what is the charge? What is the charge? Yes, what is the charge, guys? Aisha, Rabia, and Pia. So you have a capacitor. So how do we write the charge of the capacitor? Yes, guys, please be attentive. Yes, Aisha. Yes, yes. What are you saying?
So is it epsilon into epsilon by 2?
A epsilon
Like
by 2.
E,
No, not this
E,
one.
E.
So we don't know area, we don't know D. In terms of, we only know capacitance and EMF. CV, yes, yes, Aisha. So charge is CV, right? Right, everyone? Rabia and Fia.
Yes, sir.
So this would be CE. Okay. Now, what would be the energy stored? What would be the energy stored? CE by 2. Okay. So Oh, so you already told me about the this one. Yeah. So U initial is what, half, and C E square, right? And in here Q final is how much? CV, which is C and E by 2. And U final, energy stored final, is half CV square. So this is half, and
Initial is 0.
initial is what? Initial
Is it 0?
uh, final energy stored.
Sir, U initial is 0.
No, 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 no. So you have a potential, right? You have a potential. So energy stored is half CV square. So half, and C, and then this is the potential. This is not zero, right? Because it has been charged up to some potential. Whenever it was uncharged, so when it was uncharged, right, then it was zero because there was no voltage, right? There were no voltage between these potentials. There was no charge, so there was no electric field, so there was no voltage. That is why U was zero, right? But now in our case, in the initial stage, this capacitor is charged. So that's why half CV square, so half CE square. Understood, Priya?
Yes, sir.
And similarly, when we calculate, so this is E by 2, right, whole square. So this would be half, and CE square by 4. So this is U final is CE square by. So now we have all the prior information. We have the information, and so you see that initially it had a charge C, but now the capacitor has taken this much charge, C by 2. So the charge which is flowing through this one would be Q final minus Q initial, right? So the charge flowing through the battery, so charge flowing through the battery. This is delta Q, which is Q final minus Q initial. So Q final is C E by 2, and Q initial is C. So this is minus of C E by 2. So this is the charge flowing through the battery. Understood?
Yes.
Okay. Now we have to calculate work done by the battery. So work done by the battery. So delta Q is this, right? Potential into the charge. So potential is how much? What is the potential of the battery? E by 2, right?
E by 2.
Yeah. So E by 2. And then delta Q we have calculated, so C E by 2. So this is minus of C E square by 4, right? So this is the work done. Okay. Now the third thing that we have to calculate is heat dissipated. So we already know that heat dissipated is how much? This is work done total minus the change in the energy storing capacity, right? So Work done we have calculated. Now let us find out change in energy. So change in energy is U final minus U initial. So U final was how much? CE square by 8 and minus half CE square. So CE square by 8 minus half CE square. So we take the LCM 8 and this is CE square minus 4 and CE square. This is minus 3 CE square by 8. This is the change in energy, right? So now we plug in this value and we will get the heat. So minus of CE square by 4 and minus of minus which is plus 3 CE square by 8. Right, this is minus CE square by 4 and plus 3 CE square by 8. So what is the LCM of 4 and 8? This is 2, 4, 2, 1, 2. So 8. So we get this is 8. So this is minus 2 CE square and then this is 1, so 3 CE square. So we will get CE square by. So this much amount of heat is dissipated in charging this capacitor, right? Any doubt in this question, guys?
Yes, sir.
Okay, so please note down this part. So note down from here. Always remember the information that we have, so that we have to write it down. Oh, you didn't understand. Oh, so you are saying that you have no doubt. Okay, so whenever you guys want me to scroll down the screen, guys,
Done, sir.
done. Whenever you guys have noted it down, please tell.
Thanks, bye.
Noted, everyone.
Yes.
Okay, so whenever you guys have completed, please tell. Noted, everybody.
Thanks.
Done. Okay. So now, we were using the external battery, right, to charge or uncharge capacitor. Now what happens is that we have two capacitors, right? So let's say that so we have two charged capacitors. So let's say this is C1 and voltage is C1. Okay, and we have another capacitor. So its capacitance is C2 and voltage is V2. So now what we do is that this is the initial right or initial state. So what we do is that then we connect these two capacitors. So what will happen if I connect these two capacitors? What will happen? So what will happen, guys, if I connect these two capacitors? Total zero. What is total? Everything will cancel. Both are different. Voltage is different. All the things are different. We are connecting these two capacitors. So this topic is sharing of capacitors. So what will happen is that whoever has the higher potential, the charge from will flow from that and will go to the lower potential, right? So the charges will transfer. When we connect these two, then charges will transfer, and these transfer will happen until both the charges have the same potential. So they will reach the same potential, right? Because due to the difference in their potential, the charges will flow, but ultimately they will get the same charge, the same potential, right? So this will have the same potential, this will have the same potential. Is this part clear, everyone? So now we have to find out that what would be this common potential or equilibrium potential, whatever we could say, the common potential. Okay. So first, let us calculate the charge in here. So what is the charge in here?
C1V1.
Yes,
C1V1.
C1, right? And what is the charge in here?
C2V2.
C2, right? So let's say that this is initial. So initially, how much was the charge? Initially, the charge was Q1 plus Q2, which is C1 V1 plus C2 V2. This is the initial charge. Right, guys? Correct?
Yes, sir.
Now, then what? So in here, what is the charge? What is Q1 in here?
Sir, we'll take V common, so C1 plus C2.
So Q1 is C1, right? Right, in here Q1 is C1B, right? And
Yes,
in
sir.
here Q2 is how much? C2. So let me write it as final and final, or let me write it as prime, so that these are different. Okay. So the charge has been transferred, right? But what do we know about the charge? So in our first chapter, when we were studying the properties of the charges, so what were the properties of the charges? Do you guys remember? Quantization, you know, right?
Yes,
Addition,
sir. Q is equal to N in P.
yeah, so addition of charges, you know. The third one was what?
Hidden nature of charge.
Conservation of charge, right? So did you say conservation?
Additive nature.
Yeah, what did you say, Aisha? Additive. Oh, no, no. So first property was the quantization, second was additive, because if we have different charges, right, the whole would be Q1 plus something, right? So In here, we used the total charge would be additive nature. So in here, we use that property, additive nature, right? Now, the third property was the conservation of the charges, right? So initially, whatever the total charge was here, finally, the charge would be the same. Total charge would be the same, right? That is the conservation of charge, right, guys? So from conservation of charge, conservation of charges, right? We know that Q initial would be equal to Q final. Is this part clear, everyone? Is this clear?
Yes, sir.
So Q initial, we know that that is C1 V1 plus C2 V2. And Q final is how much? This is C1 V plus C2. So this is C1 V1 plus C2 V2. And as Pia was saying, we can take V common, so this is C1 plus C2. So then we can calculate V, which is what? C1 V1 plus C2 V2 divided by C1 plus. So this is the potential at which the flowing of charge would stop. Is this part clear, guys? Is this part clear?
Yes, sir.
Yes,
Okay.
sir.
So now and then, because the charges are shared, right? So then we have to calculate what is the heat dissipation, right? Because what happens is that their energy storing capacity is changing, right? So due to their energy storing capacity changes, there is some heat which is dissipated. In case of battery connecting, there was some heat dissipated due to the battery. But now we have the heat dissipated due to change in the energy storing capacity. So heat dissipated would be whatever U final minus U initial. Or we can also calculate U initial minus U final, right? So change in energy storing capacity. So change in energy store, right? This we want to calculate. So now let us calculate what was U final and U initial, and then we can calculate the change in energy, right? So from here, can you guys tell me what is U1? What is U1? Yes, this is energy stored. So half CV square, right? So half C1 V1 square, right, everyone? And then U2 is half C2 V2 square, right? So, okay, and now we have to calculate the energy on this energy stored in this capacitor. So this is, let's say, so let's say U1 prime. Oh, you are noting it down. So I will give you the time to note down, but let us first understand, right? Let us understand and then I'll give you the time. Okay, so U1 prime is half and C1 and B square. And U2 prime is half and this is C2 B square. Okay, so in this case, the capacitors are connected. Capacitors are connected, right? So they will acquire a common potential. Okay, so now we have all the values. So let us calculate U initial. U initial is half C1 V1 square plus half C2 V2 square. And U final is half and C1 V square and plus half C2 V square. Okay, so when we calculate heat dissipated, this is U initial minus U final, or we can also calculate U final minus. So this is half V1 V1 square plus half C2 V2 square and minus of half and C1 plus C2 is common and then V square, right? So this would be how much? This is C1 V1 square plus half C2 V2 square minus half C1 plus C2, and we can put the value of V from the previous. So let's say this is 1. This would be how much? So C1 V1 plus C2 V2 whole square and divided by C1 plus C2 whole square, right? This part will cancel and we will get what? So we will get half C1 V1 square plus half C2 V2 square minus half of C1 V1 plus C2 V2. Okay, so and then whole square divided by C1 plus. So now we have to simplify this, right? So let us simplify this. Half is taken outside and this is C1 plus C2. So we will get C1 V1 square and plus C2 V2 square multiplied by C1 plus C2 and minus of C1 V1 plus C2 V2 whole square. So I will simplify this further, but you guys please note it down. Okay, so let me simplify this. Because then you guys will not get a time to. So first let us simplify this. This is C1 V1 square and then we have C1 C2 V1 square and then we have C2 square V2 square and then we have C2 C1 V2 square. So this is this and then we have minus of C1 V1 square plus C2 square V2 square plus 2 C1 V1 C2 and then we have C1 plus C2. So this is half. This is a very lengthy calculation, and you guys have to just remember the final result. So I can let me. So this is and C2 square plus C2 C1 C2 square minus C1 C1 square minus C2 square and minus of 2 C1 C2 C1. So what is cancelling, guys? What is the term which has been which we can cancel? Yes, guys. What is the term that we can cancel?
Even when we want to
Yes. So this one we can cancel, and this one not. Right, guys?
know,
Okay. So then what we can? So then we have half, and we have C1. So this is C2 C1, right? C1 C2. So C1 C2 V1 square, and this is also C1 C2 V2 square minus of 2 C1 C2 V1 V2, and then divided by C1 plus C2. So can you guys tell me what is common in here? So in the numerator, we have C1, C2 common, right? And then this is C1 plus C2. So then we have V1 square plus V2 square minus of 2V1. So we will get half C1 plus C2 and C1 C2 and V1 minus of V2 whole square. So this would be the heat dissipate. Is this part clear? So these are just some calculation. Okay, and so any doubt in the calculation part or any doubt in the conceptual part? Any doubt, guys? Any doubt in sharing of capacitors?
no, sir.
Okay, so we have two capacitors, they are charged, and then we connect those capacitors. So then there will be some sharing of the charge. And due to that, we have some heat dissipated and we have some common potential. So that is what we are ultimately calculating. So you guys please note it down and then, yeah. So you guys please note it down. And if you have any doubts, so please ask. So whenever you guys need me to scroll down the screen, you guys
One second.
Yeah, so whenever you guys have noted it down, so please tell me to scroll.
One second.
Sir, can you explain it?
Oh, is this okay?
Yes, sir. Yes, sir. Done, sir. Well done.
Done. So whenever you guys have completed this much, please tell.
And
Hmm. Noted everyone.
also
Noting. Okay. Rabia and Fia, what about you guys? Noted. Fia has noted. Ashia, noted. No, Aisha. Sorry. Yes, Aisha, noted. Guys, Aisha and Rabia, noted.
yes.
No. Please note it down and tell. Okay, done. Uh, so what we calculated that whenever we are connecting a capacitor to another capacitor, both are charged, right? So both are charged, right? And remember, we are connecting the positive one with the positive one. Then we get the potential, which was C1 V1 plus C2 V2 by C1 plus C2. And then we get the heat dissipated, which is half of C1 C2 by C1 plus C2, and then V1 minus V2 whole square. Okay, but if we change the polarity, so we change the polarity, meaning that we connect we connect positive one with the negative one. Okay, so then what happens? Then from Kirchhoff law, we know that the change in potential would be negative. So then this is plus, this is minus, and this is minus, and this is plus. So then the common potential would be this one. And then the heat dissipated would be, because the potential will change. So polarity of potential will change. So then this would be V1 plus V2. Okay, so please note it down and then so this part is important. Okay. So we change the polarity. We connect positive to the negative. Okay. So please note it down and then we'll end the class. And whenever you guys have noted it all, please check.
So
Okay, Aisha, done. Tia and Rabia, what about you guys? Noted? Yes, Rabia and Pia, what about you guys? Noted? Okay, Rabia, what about you? Noted? Yes, Rabia, are you there?
Yes, sir.
Noted? Yeah, have you noted it down?